This is the 13th video that I'm making to support a course that I'm teaching in elementary number theory. And last time we looked at the notion of Euler's totient function as well as Euler's theorem, or sometimes called Euler's generalization of Fermat's little theorem. And today we want to prove some things about Euler's totient function and come up with a nice strategy for finding values of this function. Okay, so let's begin by recalling that Euler's totient function phi goes from natural numbers to natural numbers, and it's defined by phi of n is equal to the number of elements in the following set. So these are natural numbers between 1 and n that are relatively prime to n. Okay, so we did several examples in the last video of evaluating Euler's totient function at some numbers, and we'll do some more at the end of this video once we have a nice formula for this function. Okay, so the first thing that we want to prove is that phi is indeed something called a multiplicative function, but let's look at the definition of that first. A function f from natural numbers to complex numbers is called multiplicative if it satisfies two conditions. The first is that f evaluated at 1 is 1, and the second is that f evaluated at m times n is equal to f of m times f of n when the GCD of m and n is 1. So if the GCD is not 1, then all bets are off. You may not have this property. And I think this is like some sort of number theoretic definition of a multiplicative function. If you know something about abstract algebra, ring theory, or something like that, then this may seem like a little bit more restrictive. But let's just keep the context of this being a number theory class. So we need this second condition here. That's important. Okay, so let's get going on this proof. We'll start by proving that the first condition holds, but that's pretty easy. Notice that phi of 1 is the number of elements in the set containing just 1. Well, why is that? Well, 1 is the only number between 1 and 1 that has GCD of 1 with 1. So we're pretty good to go there. This is equal to 1. Okay, so now we want to suppose that we've got a pair of relatively prime natural numbers. So I'll call them m and n. And like I said, they're relatively prime, or in other words, their GCD is equal to 1. And now let's recall in the last video, we had the notion of a reduced residue system. And we're going to want to use that notion for these two numbers m and n. So let's bring two reduced residue systems into existence. So A1, A2, all the way up to A phi of m, and then B1, B2, all the way up to B phi of n. So these are reduced residue systems mod m or mod n, kind of as the context dictates. So obviously this first one is going to be a reduced residue system mod m, and this second one is a reduced residue system modulo n. And now we're going to prove the following claim, and this following claim will actually pretty much finish this proof off. So the set of linear combinations AJN plus BKM, as J and K run over the appropriate indexing sets, so we get everything from these two sets. So let's see, that means J must go between 1 and phi of m, and then K must go between 1 and phi of n. So this is the set that we're looking for, and our claim is that that is a reduced residue system modulo mn. Okay, well, let's see maybe how this would help. So this is a reduced residue system modulo m, and how many elements are in there? Well, there are phi of m elements in there. This is a reduced residue system modulo n. There are phi of n elements in here. But then by the construction of this set contains phi of m times phi of n elements. So if we can prove that it's a reduced residue system modulo mn, then that means phi of mn is the size of this set, which is phi of m times phi of n, and then we're good to go. Okay, so we'll start the proof of this claim with a couple of observations. So first off, the GCD of AJN plus BKM with the number m is the same thing as the GCD of AJN with m. So why is that? Well, that's from one of the properties of the GCD that we proved several videos ago when we were looking at the Euclidean algorithm. So notice here we've got a multiple of m. If we take this multiple of m away, then all we're left with is the GCD of this number and this number. But next, let's notice that AJ is relatively prime to m, given that it's an element of this reduced residue system. N is relatively prime to m. That's by our given up here. That means the product is relatively prime. So that means we've got a GCD of 1 right here. But now we can symmetrically play this game having an n here instead of an m here. So we've got the GCD of AJN plus BKM with n is the same thing as the GCD of BKM with n, which is equal to 1. Again, kind of symmetrically for the same reason. But now let's look at what we've got. So we've got the GCD of this number right here, which maybe I'll underline in pink, with the number m is 1. And then this number that I'll underline in purple, which is the same as the number in pink, has a GCD of n with 1. But if those two pairs are both relatively prime to m and n, then they are relatively prime to the product of m and n. So again, that's one of the properties of the GCD that we proved early on. So notice that means that we have the GCD of AJN plus BKM with mn is equal to 1. And that's one of the properties we need for this set to be a reduced residue system. Okay, so let's maybe summarize what we've got at the top, and then we'll move on to the next step. Okay, so where are we along the path of this proof? We started with a reduced residue system mod m and another one mod n, and we constructed this would-be reduced residue system modulo the product m times n. So far, we've shown that this GCD of AJN plus BKM with mn is equal to 1. So the GCD requirement of being a reduced residue system is good to go. Now we just have to show that all of those things making up that set are incongruent, and we have enough of them. So let's do this part first. We want to show that all of these are incongruent modulo mn. So let's start by supposing that we've got two of these that are congruent. So I'll say AJN plus BKM is congruent to ARN plus BSM. And this is occurring modulo MN, like that. Okay, well, let's move some things around. So we've got a multiple of n on one side and a multiple of m on the other side. So that's going to give us something like AJ minus AR times n is congruent to BS minus BK times m. And that, again, is all happening mod mn. So that's just moving this AR over and that BK over. Okay, but let's see what we've got. The left-hand side is a multiple of n. The right-hand side is a multiple of m. But n and m are relatively prime. But that tells us that the multiple of m that's occurring on the left-hand side must be wrapped up in this AJ minus AR. because since the right-hand side's a multiple of m, so is the left-hand side. And then furthermore, the multiple of n that occurs on the right-hand side is wrapped up in this bs minus bk. Again, because the left-hand side is a multiple of n, so is the right-hand side. We're only able to do that because these two numbers are relatively prime. Okay, so let's summarize that split as follows. We have aj minus ar is congruent to 0 modulo m. Like I said, it's a multiple of m. And then likewise, bs minus bk is congruent to 0 mod n. Okay, so that appropriately summarizes that discussion that I said in words. Okay, but now we can like move this stuff around a little bit. We get aj is congruent to ar modulo m, and then bs is congruent to bk modulo n. But now let's recall, since the a's form a reduced residue system mod m and the b's form a reduced residue system modulo n, then that means they are either equal or incongruent. Well, since these things are congruent, then they must be equal. That's part of it being a reduced residue system instead of maybe just a residue system. Okay, so that tells us that j is equal to r, or maybe aj is equal to ar, but really the indices being equal is enough. And then this down here implies that s is equal to k. But now if j is equal to r and s is equal to k, then that means we don't just have congruence up here, but we have equality up here. So we've got ajn plus bkm is equal to arn plus bsm. Okay, so let's back up and summarize. So this fact that the GCD of this object with m and n is equal to 1, that means one condition of the reduced residue system is satisfied. The fact that the only way for these to be congruent mod mn is for them to be equal is another part of the reduced residue system to be satisfied. But that actually doesn't finish the proof of this. That only gives us an inequality. So far we see that phi of mn is bigger than or equal to phi of m times phi of n. So let's recall that our set of phi of m times phi of n numbers were made up of numbers of this form. So we showed that we have the GCD requirement and congruence implies equality, but we haven't yet showed that we have enough of the elements in that set. So that's the last thing that we need to show. But we don't have room for that, so let's get rid of that and then we'll do that proof. Okay, so far we've proven that if we've got relatively prime natural numbers m and n, that phi of mn is bigger than or equal to phi of m times phi of n. And that involved constructing what is a would-be reduced residue system modulo mn out of reduced residue systems modulo m and n. And what is left to do is show that our hopeful reduced residue system is big enough. So in some ways we've shown it is not too big already. Now we want to show that it's big enough. Okay, so let's see how we can do that. So we're going to bring a new integer into the world. We'll call that c. So let's suppose c is an integer such that the GCD of c with m times n is equal to 1. So keeping in mind where we want to go, what we hope is that c is congruent to something from our would-be reduced residue system modulo mn. Because remember, our hopeful reduced residue system should have all possible residues that are relatively prime to mn, including this random one c that we just picked. Okay. But what should you do if you see that the GCD of c with mn is equal to 1? Well, you should maybe implore something called Bézout's identity, which we do all the time. So now we want to use the fact that m and n are relatively prime. And so let's use Bézout's identity. So in other words, let's take integers x and y such that mx plus ny is equal to 1. And again, that's possible because the GCD of m with n is equal to 1. But now let's notice that this means that the GCD of m and y is also equal to 1, because we've got a linear combination of m and y that creates 1. And likewise, the GCD of n with x is also equal to 1. So even though x and y were kind of brought into existence to create this, which uses the structure of m and n, we get this extra stuff kind of for free. Okay, so now let's look at the following observation, which will be helpful. And that is that the GCD of cy with m is equal to 1. And then likewise, kind of in parallel, the GCD of cx with n is also equal to 1. Okay, so let's run through the little proof of this observation really quickly. So let's suppose P is some prime and P divides C times Y and P divides M. In essence, what we're doing here is starting by assuming that the GCD is not 1 and searching for a contradiction. Okay, so from here, we can say that this means P divides C or P divides Y. That's just a standard fact about prime numbers and when prime numbers divide products. Okay, so now let's see how we can work off of both of these. So this splits into two cases, P divides C and P divides M, or P divides Y and P divides M. But now we can do a bit of a trick. If P divides M, then P most definitely divides Mn just by multiplying by n. Okay, but now we know the GCD of C with Mn is equal to 1. That's our assumption way up here. So this tells us that P divides 1, but there are no primes that divide 1, so that leads us to a contradiction. Now we move over here and we see that P divides Y and P divides M, but this says that the GCD of M and Y is equal to 1, but that means P divides 1, but again, that's a contradiction because there are no primes that divide 1. So that means there are really no primes that divide both CY and CM, but the only way for that to be the case is for this GCD of CY with M to be 1. And then symmetrically, we have the GCD of CX with N is also 1. Okay, so let's leave this observation up, but we'll get rid of this proof and then finish this off. Okay, we just got done arguing this observation. This is going to be key to finishing this off. So since the GCD of CY with M is 1, then that means that CY is congruent to one of the elements from the reduced residue system of M. And so remember, those were of the form A sub something. So we'll say A sub J mod M. And remember that J is going to go between 1 and phi of M. And then similarly, this over here says that CX is congruent to B sub K modulo N. Again, because we've got this reduced residue system. And now we're actually ready to start finishing it off. So let's multiply both sides of this congruence by n, and notice that that tells us that aj times n is congruent to, let's see what we've got, cy times n modulo m. And now we've got all of the pieces in place to start finishing this off. So let's take this congruence, which followed from our observation, and multiply it by n. So notice that that is going to give us c times ny is congruent to aj times n modulo m, like that. And then from here, we can freely add a multiple of m to the right-hand side. And that doesn't change anything because m is congruent to 0 mod m. So notice this is going to be congruent to ajn plus bkm mod m. Again, we just multiplied this fancy version of 0. But now let's look back up at this equation right here and reduce this equation modulo m. So this bit will go to 0, and we'll have n times y is congruent to 1 mod m. So that means this n times y multiplies down just to the number 1, well, mod m, and we're left with c is congruent to this ajn plus bkm mod m. And then through a very similar, or in some ways a parallel argument, we get c is congruent to the same thing, ajn plus bkm mod n. But then since m and n are relatively prime, that tells us that c is congruent to ajn plus bkm mod mn. But that tells us that our reduced residue system is in fact big enough. So in other words, we have phi of mn is less than or equal to phi of m times phi of n. But now combining this inequality, which I've just circled down there, together with our inequality from the first half of the proof, we see that phi of mn is equal to phi of m times phi of n, which is exactly what we needed to show for phi to be multiplicative. Okay, so now that we've got this in place, we need to prove a lemma involving the value of phi at a power of a prime, and then we're pretty much good to have a formula for our function phi. Okay, we just got done proving that our function phi, Euler's totient function, is indeed multiplicative by this definition down here. Now we want to see the value of phi at a power of a prime. That'll give us a nice calculational method for calculating phi at some like randomly given number. Okay, so if p is prime, then phi of p to the r is equal to p to the r minus p to the r minus 1. And this proof is a lot shorter than what we just saw. And we can start by noticing that phi of p to the r is equal to the number of elements in the difference of the following sets. So 1, 2, 3, all the way up to p to the r minus all multiples of p. Well, recall that we want to count up all of the numbers that are relatively prime to p to the r, but the only thing that's not a relatively prime to p to the r are multiples of p. So that's kind of how that settles out. So now let's count up all multiples of p. That shouldn't be too hard. So notice we've got 1 times p. That's most definitely a multiple of p. We've got 2 times p, 3 times p, all the way up to the last multiple of p will be p to the r minus 1 times p. So now we're good to go. We need to find the number of elements in this set minus this set, which is a subset of the original set. So here we have, there are obviously p to the r elements in this first set. And then the elements of the second set can be counted by the coefficients of p. So there are p to the r minus 1 elements in that second set. And that finishes the proof of this lemma. Okay, so now let's smash that last theorem and this lemma together into a nice formula for phi. Okay, so this is the punchline of this video, and that is the following corollary. So if we've got a prime factorization of n, which we know is possible by the fundamental theorem of arithmetic, and that prime factorization is p1 to the r1 all the way up to pk to the rk, where all of the p's are distinct primes, then phi evaluated at n is n times 1 minus 1 over p all the way down to 1 minus 1 over pk. Okay, so let's see the proof of this, which is actually fairly calculational and quick now that we've got our previous theorem and that corollary. So let's notice that phi of n can first be written as phi of p1 to the r1 times phi of p2 to the r2 all the way up to phi of pk to the rk. And that's by the multiplicativity of our function phi. All of those primes are clearly relatively prime to each other. Now we can apply our prime power formula to each of these. So notice this guy right here will be p1 to the r1 minus p1 to the r1 minus 1, all the way up to pk to the rk minus pk to the rk minus 1. Again, that's by our previous lemma. Now what I'll do is factor the first term out of each of these binomials. So I'll factor a p1 to the r1 out of this one, a p2 to the r2 out of this one, and finally a pk to the rk out of the last one. That's going to leave me with a p1 to the r1, p2 to the r2, all the way up to pk to the rk in front of the whole thing. Then let's see what's left over. So here we'll be left with 1 minus 1 over p1. Well, why is it 1 over p1? Because we have 1 less power of p1 here than we factored out. And then the next term will be 1 minus 1 over p2. All the way up, the last term will be 1 over 1 minus pk, like that. But now we're in luck because notice these numbers represent exactly the factorization of our number n. So we can just smash all those together to get n, and we've got n times that product over there, which is exactly what we wanted to show. Okay, so now let's do some examples. Okay, so let's do some fairly quick examples. So let's first calculate phi of 12 using our formula. So we know that this is 12 times 1 minus 1 over the primes that divide into 12. Notice we don't even really need to know the prime factorization. We only really need to know which primes divide into this. We don't need their exponents by that trick of the formula that we saw before. So we know 12 is divisible by 2 and 3. Those are the only primes that divide into it. So this should be 1 minus half and then 1 minus third, like that. But notice that's going to give us 12 times half times 2/3. I'll let you guys multiply that out and see that you get the number 4, which checks out because the only numbers between 1 and 12 that are relatively prime to 12 are 1, let's see, 5, 7, and 11. Okay, so now let's do phi of 100. We'll get 100, and then 2 and 5 are the only primes that divide into 100. So we've got 1 minus half and then 1 minus fifth. So again, that's a fairly elementary arithmetic problem, and you'll see that we get the number 40. Then finally, phi of 36, that's going to be equal to 36, 1 minus half, and 1 minus third, pretty much for the same reason as we had up here. Those are the only primes that divide into that, and that gives us the number 12 in the end. Okay, so let's do one more example before we present some warm-up problems. Okay, so now we're going to do a little bit bigger of an example. So our goal is to determine all natural numbers n such that phi of n equals the number 8. Okay, so let's first recall that our phi of n will give us p1 to the r1 minus p1 to the r1 minus 1, all the way up to pk to the rk minus pk to the rk minus 1. But now instead of factoring this the way we did in the proof of our lemma, let's factor it a little bit differently. Let's factor this term out. So we've got p1 to the r1 minus 1 times p1 r1 minus times p1 minus 1 all the way up to pk to the rk minus 1 times pk minus 1. So the important takeaway here is that 1 less than all of the primes dividing n must divide phi of n. So maybe we'll put that as a note. So if p divides n, and I should say p is a prime, then p minus 1 divides phi of n. Okay, but now we can look at some divisors of 8. Remember, our goal is for phi of n to be 8. So if p minus 1 divides phi of n, which is 8, then that means p minus 1 comes from a fairly small set. There are only so many divisors of 8. So it comes from the set 1, 2, 4, 8. Again, those are all the divisors of 8. But that tells us that p comes from the set 2, 3, 5, 9, but we can immediately get rid of 9 because it's not prime. Remember, p is a prime dividing n. Okay, so what does that tell us? That tells us that the prime factorization of n that will achieve phi of n equals 8 only includes the numbers 2, 3, and 5. In other words, our number n looks like 2 to the a times, let's see, 3 to the b times 5 to the c. Okay, so now that we've figured that out, let's maybe bring that data to the top and then we'll move on. Okay, so our goal is to find all natural numbers in n such that phi of n is equal to 8. So far, we've argued that n has to be the form 2 to the a, 3 to the b, 5 to the c. 2, 3, and 5 are the only possible prime factors of n. And now from here to the end is not super fun. It's just a bunch of casework. But I want to point out that a lot of times math problems end up with a portion of the solution which is not fun. And maybe I shouldn't say not fun, but maybe just a little bit tedious. And that's just part of the game. So our first case is that c is equal to 0. So in other words, n is equal to 2 to the a times 3 to the b. Now, like I said, we're going to do casework, including subcases. So let's do our first subcase, which will be a equals 0. So notice if a is equal to 0, then that tells us that n is equal to 3 to the b, which tells us that phi of n is equal to 3 to the b minus 3 to the b minus 1. And we want that to be equal to 8. So 8 must be a difference of 2 powers of 3. And those are consecutive powers of 3. Now, there are a couple of ways that you can figure out that is impossible, but let's maybe just go ahead and factor out the 3 to the b from this, and notice that this is equal to n times 1 minus 1/3. So that's like also by our formula for phi of n, we need that to be equal to 8, but that tells us that 2 over 3 times n is equal to 8. But notice that gives us that n is equal to 12. But now, since all of this is all kind of funny business, we probably need to check. But phi of 12 is equal to 4, which is not equal to 8. So that means we do not get a solution in that case. Okay, so now let's move on to our second subcase. So I'll call that subcase 2. And that will be when b is equal to 0. So in other words, n is a power of 2. It's 2 to the a. Okay, so now we can do essentially the same thing that we did before. We know phi of n is equal to n times 1 minus half, but it's also equal to 8. But notice that tells us that a half n is equal to 8, or in other words, n is equal to 16. But then you can check using our formula for phi of n that phi of 16 is good to go. Well, first of all, we see that our assumption really built into this was that n was a power of 2, but 16 is a power of 2, which means we're good. Whereas over here, this didn't work for a couple of reasons, but this says that n is 12, but our assumption was that n was a power of 3, and those are not conducive to each other. Okay, so now let's look at our third subcase, and that will be neither of these are equal to 0. And so we've got a and b are non-zero. Okay, well, from there, we've got that phi of n is equal to n times 1 minus half times 1 minus third. But let's see, that means that n over 3 is equal to 8. Well, you might say, well, why that? Well, that's just from standard like multiplication of rational numbers there. But if n over 3 is equal to 8, that tells us that n is equal to 24. But notice 24 is most definitely of the form 2 to the a, 3 to the b. But you can also just run it through and see that phi of 24 is also equal to 8, which was our goal. Okay, so let's maybe summarize what we have so far up here. So we see that n equals 16 works, and n equals 24 also works. And I think that's maybe enough to do on this example. Maybe I'll leave it as a warm-up to check the other cases. Okay, so I'm gonna leave you guys with a couple of warm-up problems. So the first is to find phi evaluated at 250 using the formula that we developed in this video. The second one is to find phi of 1,124, again, using the method that we constructed in this video. And then next, similar to the example, find all natural numbers n such that phi of n is equal to 10. And that's a good place to stop.